All right, let's get started. Hello, everyone, and welcome to the September 2025 Link Tech Talk. My name is Mi Dai, and our co-host is Colin Chandler. We are Link Frameworks project scientists. I'm at University of Pittsburgh, and Colin is at Dirac Institute at University of Washington. So Link Tech Talk includes presentations and demonstrations that showcase work done by the broader Rubin software and archive community with goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, Tech Talk highlights the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. Today, we're hearing about an overview and update from the Link Frameworks team in year 3 from Jeremy Kubica. Jeremy is the Director of Engineering of the Link Frameworks team. He started working with astronomers while completing PhD in robotics at Carnegie Mellon, and he spent over 15 years working on large-scale machine learning and software engineering problems at Google. His research interests includes machine learning and scalable algorithms data structures. He is also author of multiple fun introductory computer science books. For the talk, please ask questions in Zoom or in the Link Tech Talk channel. On Zoom, you can type questions in the chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel. With that, Jeremy, please take it away.
Hi, so welcome. I am Jeremy Kubica. This is going to be two types of talks merged into one. One is going to be an introduction to Link Frameworks or a reintroduction to people who are not familiar with the team. The second point for people who are familiar with the team, we're going to provide an update of what specifically we've been working on for the past year and a half to year, with specific focus on DP1. So, quick outline of the talk. I'm going to start off with the standard introduction to what is the Link Frameworks team, what's our mission, what are we trying to accomplish. Then do a little bit of a deep dive into one particular problem we've been looking at for a while, which is scalability and software for spatial matching. Then I'll take a step back and look at all of our core projects and provide a very brief overview to give all of the listeners a chance to kind of understand the breadth of what we're working on. And I'm going to finish up talking about our incubator program, how astronomers can get involved with this, and how we can collaborate together. So the Link Frameworks team is a multidisciplinary team whose mission is to enable science by developing scalable and productionized software and algorithms in collaboration with the broader Rubin community. And if we dig down on what this means, it means our projects were really trying to be impactful to a broad portion of the community. We want our software to be used not just by a single research group, but rather to be used by many research groups. We want to build on and with Rubin tools, avoid unnecessary duplication. There's a lot of incredible work that's already going on both within the astronomy open source community and within Rubin DM in particular. And we want to take advantage of that and have all of the work we do be additive to that. We try to be very collaborative while doing this. Our focus is, due to the nature of the team, is primarily on the engineering and algorithm side. We write a lot of software. We tend to focus on questions of scalability, productionization, also usability and configuration is something we've started to look at more and more, of how can you adapt software to make it more modular, to make it so that way people can extend it. Everything we do is open source software. It doesn't have to be our own software as well. A lot of what we can do is contribute to existing software packages if they are a good match for the type of work that we're doing. The team, as I said, is a multidisciplinary team. It's made up of a combination of software engineers who largely have industry experience and sit on the computer science side, and research scientists who are astronomers, astrophysicists, and bring in the research experience. And this tight coupling of research scientists and software engineers has provided a huge advantage in terms of the two groups being able to work with each other and share ideas and function as one team. And it's something we're really excited about in terms of how our model has worked out. So we contribute to the astronomy community really in three main ways. One is core projects, and these I'll talk about next. These are long-running open source projects that are primarily led by or invested in from multiple engineers in our team, multiple research scientists as well. In addition, we run incubators, which I'll talk about at the end of this talk, which are focused 3-month collaborations on projects proposed by researchers. And I'll talk about the process we use for that and how people can get involved. And then finally, we do a little bit of education and coordination work when there are pieces of software or pieces of software best practices where we feel like we can add benefit and provide value. Sometimes we'll step in there. So let's start as a motivating use case looking at the question of cross-matching. And this was one of the first use cases that we came across when scaling up the team and looking at what are the problems we need to actually address. Now, the motivation for this, for anybody on this talk, is not going to come as a surprise. We're seeing a huge amount of data that is starting to roll in from not just Rubin, but other observatories. Rubin is finishing up the commissioning phase. It's moving into science validation. We're going to be seeing a large number of images come in. We're talking 5 to 10 petabytes of images per year, tens of billions of stars and galaxies. And then this is going to be repeated imaging of the visible sky over 10 years to present a color movie, 10-year-long movie of the night sky. Huge amount of raw data, huge amount of catalog data once we boil this down to stars, galaxies, and asteroids, and just a vast number of individual observations. And this isn't the only observatory that is coming online. In addition to Rubin, there is the Roman Space Telescope, which is in construction, due to be launched, the Square Kilometer Array, and there's actually a bunch of other ones here. These are just 3 examples. And this just is going to fundamentally change the paradigm of how a lot of astronomers work with data. None of these are going to be cases where it's possible to just download the entire data set to your local machine and run analysis on it. You have to bring the computation to the machine. And this introduces new computational challenges and new algorithmic complexities that our group is trying to address. So the example I'm going to start off with is spatial cross-matching. This is just a question of, given 2 catalogs, which entries are actually the same object. So you can see 2 examples, one on the left called catalog A, one on the right called catalog B. And each catalog is effectively just internal ID, which is going to be different per catalog, some right ascension, some declination, brightness information, and a whole bunch of other columns. But we just want to say, based on the right ascension and declination, the position on the sky, which of these objects match up. And sometimes it's relatively easy. There's a one-to-one match. You have an object in catalog A that's very close to an object in catalog B, and we can say pretty confidently, yes, this is the same object. Sometimes it's a 2-for-1 or more, many-to-one, or even a many-to-many where there's ambiguity. And it presents an interesting algorithmic challenge of how do you actually determine which object links to which other object. But the more interesting, or the more immediate question, I should say, beyond just how do we do the association, is how do we do this efficiently as we start to talk about billions and then tens of billions of objects? It's no longer possible to run a double for loop through where we're saying for every object in catalog B compared to every object in catalog A, and actually try to exhaustively compute all of the metrics such as distances that we want to compute. So we need to do this much more efficiently. And this is the type of project that the LINCC Frameworks team focuses on. And this question requires looking at the algorithms, looking at the software on different levels. You have the core algorithm, the core computation of, given 2 objects, how do you determine if they're the same? But then when you start talking about billions of objects, now all of a sudden you want to distribute the computation over many machines so you can take advantage of parallelism in the problem and make things run much faster. And this starts to lead to questions about data format and storage. How do we store the data in such a way that we can efficiently access it in this distributed format, not having to send the same 200 terabyte file to each one of the working worker computers? And then a question of flexibility. As I mentioned, there's many different ways of doing the actual cross-matching. How do we design a system that allows a user to plug in their own cross-matching algorithm in such a way that they can test it out against other cross-matching algorithms? So the work we've been doing within the LINCC Frameworks team falls into two main pieces of software. The first one is the storage format that we have built for representing spatial data. And this is called the HATS for Hierarchical Adaptive Tiling System. And I'll describe that on the next slide. And then there's LSDB, which is a framework, computational framework we've designed to actually process the HATS data in parallel over a large amount of data. So digging into HATS first, HATS is a way of partitioning the data into independent files that are spatially coherent and have approximately the same number of objects. And this is important for distributed computation because we really want to be able to give any individual worker task a unit of work that is roughly the same size. And so in cross-matching, that might be approximately the same number of objects. And we want to partition into separate files so we can load them independently. We don't have to load everything into memory at once. Anybody who's tried to load a multi-terabyte CSV file has seen the difficulties that can come with that and the challenges that you would face with that. Databases are another way of doing this, but can be potentially slow. So instead, HATS is a file organization system that is built on top of the Parquet format. And Parquet is a standard format which has a lot of advantages in terms of how the data can efficiently be accessed and is well supported by a bunch of libraries. It uses the HelPix tiling system, which for those of you in astronomy, you may have heard of this before. For those of you on the computer science side, it's effectively like a quad tree based on the surface of a sphere in such a way that the divisions have equal area as you partition them up, which handles the edge cases around the poles gracefully. So it's designed to have these equal area partitions at each level. We use this to actually subdivide the levels where we divide at a finer grain when there are more objects in that spatial area. So if we go back one slide, you can see for the areas around the galactic bulge where there's a high density of objects, we have very small fine-grained pixels, which have a lot of objects per pixel. Now, one of the advantages of the HATS format is that we are, by dividing by object and spatial coherence, we end up effectively organizing the data into light curves. The observations from the same object are put together in a nested data frame, and I'll talk a little bit about what nested data frames mean. We have a lot of data available for a range of surveys. As we've been developing this and applying it to different surveys, we've taken a bunch of the existing surveys which have public data. You can see a partial list off to the right here, and put them into HATS format, and they're available on data.lsdb.io. And we've been working with IVOA to standardize this format. There's an IVOA note that has recently been published at the link provided. Putting the data into spatially coherent files is only part of the actual task, though. We want to then take two different sets of files and actually try to do the associations between them. And in order to do this, we need an orchestration layer that breaks up the work and distributes over multiple machines. This is what LSDB does. It's actually more general than cross-matching. The idea behind it is it uses a technology called Dask to parallelize computation over a variety of machines. It provides a pandas-like interface to the user, so it's hopefully relatively easy for a user to pick up and start interacting with it. And it uses lazy evaluation of a task graph. So a user can define a bunch of steps that they want to process the data in relative quick time and then kick off the distributed computation all at once. And it won't start the computation till the user explicitly tells it to do that. And that allows a more interactive construction of the tasks to do without waiting at each state. It's built on top of the HATS format for spatial structure to improve the efficiency. So what does this look like for cross-matching? Well, if we've got the data divided up into these spatially coherent regions, what we're interested in doing cross-matching is taking overlapping regions and saying, is there an object in catalog L, the left side, and catalog R that match? And so we can take each pair of overlapping regions, as shown by this diagram, and actually process it on a separate computer. And that's what the little chip icons in the center mean. We're taking the pairs and we can process them relatively independently. And this allows a very high level of parallelism. And as you can see, these are not one-to-one matching. Sometimes you'll have a large pixel in one survey that maps to multiple smaller pixels in another survey. And so LSTB handles the intelligent association of pixels in such a way that the processing is consistent. Now, I'm glossing over a lot of complexity that we've gone through while looking at this problem. I'll mention some examples. These are the things that I get really excited about from the computer science side that make the problem a lot of fun. I'm not going to go into technical detail about exactly how we solve all of these, but they give you a flavor of the types of exciting challenges there are. So the first one is if you partition things into pixels, the closest object to the best match isn't actually guaranteed to be in the same pixel. You have to draw the line somewhere, and the true nearest neighbor might actually be right over that line. And so we can mitigate this using a caching strategy called margin data, where we store some additional data, but it provides some interesting space computation cost trade-offs in terms of
We can't hear you now, Jeremy.
how about now?
Yes.
Where did I cut out?
Good question. I think 1 minute ago.
Okay.
If you pull up the slide, I think it's this one. Yes.
All right. Apologies for my connection dropping out
just
there.
after talking about the margin caching.
After mentioned margin, great, awesome. So another difficulty is the level of partitioning. Different catalogs are going to contain different densities of sources, especially if you're looking at things at either different depths or in different bands of frequency bands. And so when combining, it's not just a one-to-one match, as I said before, and it's not even a one-to-one match with what you're processing and the output. You might want to bin differently. And so there's a lot of fun that goes into actually deciding, okay, how do we match the partitions, and then how do we determine the output partitions based on the input partitions we matched. Now, as we've been developing this, we've been applying it to a range of problems to make sure it works, to make sure it scales up, and we've seen some really nice results. We're able to run light curve feature extraction over large surveys like ZTF at scale, where we're just going through and processing all of the light curves in the data just to see what we get out of them. We ran this on the DP1 data and to look for new and known transient and variable sources. And there's a paper on arXiv that discusses this. And we worked with some external collaborators via our incubator program to use this to actually estimate stellar distances by the color shift you see from dust extinction for sources within our galaxy. They've also got a paper about this. So that's just one example of the types of projects we work on and some of the motivation about why we feel like computer science can be really important and really helpful to enabling astronomy. I'm going to now go through and present more of a high-level, very quick overview of some of the other projects we did to try to give people an idea of what's out there, what tools we can use. We're very interested to hear about where the computational pain points and bottlenecks are that people are facing, so we know what we can work on that would most help other astronomers. So please feel free to reach out and say, yeah, you're not solving the problem we need to have solved. There's this entire case of problems that, are out there. So very quick preview. These are the ones I'm going to run through. I've already talked about scalable spatial analysis. For a full list of our software, you can go to our webpage. This is a long address, but basically we are off the LSST Discovery Alliance site. There's a subpage called Areas of Focus where we list out not just the software, but also provide links to GitHub and links to read the docs. So one of the other initial motivating use cases that we started looking at when we started up the team was large-scale time series analysis. And initially, this was a separate effort than spatial analysis. And over the past couple of years, we've merged them. And in doing this, we went through several iterations of what the time series analysis libraries would look like, and ultimately settled on an approach called nested pandas. And this provides an ability to take a data frame like light curve information, where you have time and flux values, and nest it within another data frame. So each row here of the outside data frame might have object level information, the right ascension, the declination, and then within one column have another nested frame which tells information about the light curve over time. And the goal was really to provide an easy to use distributed framework for analyzing time series. So the pandas for light curves. And we wanted to do this in such a way that supported user-defined algorithms, especially algorithms that follow the form of apply this to each row. So apply this to every light curve in our data set. We wanted to use Dask to enable distributed computation. And ultimately, what we realized is for a lot of the computational framework, we were building similar structures as LSDB. And so we merged the two projects. Nested Pandas is now a fundamental component and one of the libraries used within LSDB. And it's also a standalone library. So if you're not looking for all of the surrounding infrastructure of LSDB, you can actually use Nested Pandas just to do kind of traditional pandas-like operations, but LSDB provides the scalability via Dask, the organization via spatial partitioning. We also are looking at supporting non-time series data, such as spectra. We know there's other things people want to nest other than light curves. We want to support that and just provide a general usable kind of multi-layer pandas data frame. Again, this was a core part of the analysis that we ran on the DP1 data. We actually used the Nested Pandas library as part of the time series analysis to find interesting new transient and variable sources. In addition to analyzing the data of what we've actually seen, one important question that keeps coming up is what should we be seeing or what could we be seeing? So another effort we've been working on is simulating time-varying phenomena with the goal of providing easy, efficient, and extensible framework for doing this simulation. So the idea being maybe we want to evaluate survey strategies of say, could we see this type of phenomena given a proposed survey cadence? Or we want to generate data to test our detection and classification algorithms. A lot of machine learning algorithms need an evaluation set, and so starting with simulated data provides a first step towards moving toward the full production. Or maybe we want to analyze the selection function and quantify or mitigate the bias in analysis. Maybe we are filtering out too much of a population of one object based on our survey strategy. And one way to know this is to actually go through and simulate what we should be seeing. And then we could perform simulation-based inference, running many simulations to actually try to figure out what the underlying physical parameters are. This is an example from an earlier paper. This is actually something using SNANA, but shows the flow of this type of simulation that we're going for, where we want to produce a realistic spectral energy distribution based on the physical characteristics of the object. run it through realistic effects like redshift and dust extinction, and then figure out how it goes through the survey filters to actually produce the passband information, and then what noise would be applied when it actually hits the detector. And so this is the general flow that the software uses. Continuing on in this high level kind of list of things we've been working on, another project we've been working on is photometric redshift estimation. And this is an interesting project because it's, as I mentioned, a project where we're contributing to an existing ongoing code base. So the Dark Energy Science Collaboration has a software package called Rail for redshift assessment infrastructure layers that is meant to provide basically 3 pieces of functionality for running controlled experimentation in such a way that it's very easy to add modules. So the first one is creation of realistic mock data. So you can forward model what redshift data should look like. The estimation by running many different algorithms. There are a lot of different photometric redshift algorithms that may perform differently in different types of objects or different scientific analyses. And you might want to run 10 of them at once and actually compare how they perform in order to understand which one is best applied to your problem. So this wraps them in a common API. So that way you can run all of the algorithms without having to become an expert in how to install and run each one. And then finally, evaluation. If you're running 10 algorithms, you really want to know, how do they perform? So this allows you to compare the estimated redshift from your models with ground truth when it's known, or compare rough metrics when the ground truth is not known. Hyrax is a newer effort that we've been working on to try to lower the bar for complexity of machine learning in the astronomy domain and really make it a lot easier for an astronomer to pick up a machine learning tool and apply it to their problem. And the illustration off to the left shows kind of the entire ecosystem of considerations when you're deploying a new machine learning algorithm. It's not just the ML code, which is the little box with the red outline, but how do you load the data? How do you compare your models? How do you extract the features? How do you monitor this as it goes? And Hyrax is meant to address all of these problems in a way that makes things easier. For example, effortless scaling, being able to run code on a laptop and then move it over to a data center with GPUs. Get the data in the first place. We've been working on survey-aware data downloaders to extract cutouts from, for example, HSC. Organize the data into a cohesive structure where people can actually figure out where their data, where their results is stored, and use that efficiently in either analyzing or doing new runs in the future. We want this to be very extensible, open source, allow users to bring in their own models, their own data sets, and to build off the large number of really excellent tools that exist out there. So visualization is a really good example where there's a lot of great visualization tools. Each one requires some amount of expertise and knowledge to figure out how do you plug that into your data. Well, we want Hyrax to make that easy so that way you bring your data and the visualization can happen. So if you look at the pipeline of training a machine learning model and using it in analysis, the blue boxes represent bottlenecks that Hyrax is meant to address. So for example, you collect data off a telescope, you need to download it, you may need cutouts of individual objects. Then you want to take those cutouts and train many, many machine learning modules, and there's some configuration and setup required for this. Then you want to evaluate their performance on a bunch of standardized metrics, which one is actually doing the best. You might want to then predict on new examples or maybe visualize what you've got to try to find some structure in the data. You might want to do something like similarity search, where you're saying, here's an interesting object, what else in the data set look like it? And ultimately, we really want to be driving this discovery. We want to make it so that way astronomers can run whatever analysis, whatever sort of exploration they want to, without having to spend days and days and days learning about the configuration of each component. All right, another project I'll talk about, which is a slightly different type of project than the other ones I've mentioned so far, is work we've been doing on detecting very faint solar system objects. And this is an algorithm that was originally developed at the University of Washington. It's called kernel-based moving object detection, or KB-MOD. The idea is being that if you have a very dim object moving, you might not be able to see it, or it might not rise above the detection threshold in any single image. But if you were to account for the velocity and shift all the images to account for the velocity and stack it up and do an image stack, all of a sudden the object would appear. And that's what's shown in the rightmost example. Now, how do you know the velocity? The truth is you don't. So KB-MOD specializes in very tractably searching many, many, many different trajectories and then using statistical estimation to try to figure out which ones actually correspond to a likely object. Um, the reason I say this is slightly different than the other projects is it's an example of a piece of software where we think the main contribution is going to be the data products coming out of it. Our goal is to produce catalogs of TNOs that can be used in solar system analysis, as opposed to necessarily software that hundreds of people will use. We hope that the data products will be the final products coming out of this. The final aspect I'm going to talk about today, I see there's a couple questions. We got once the name Hyrax. Do we have anyone from the Hyrax team who can very quickly weigh in on where that came from? Okay, I do not see anybody from the Hyrax team. It is an acronym. I don't remember what it stands for, but it also is a incredibly like furry mammal thing that is cute that kind of looks like an oversized um I don't know, oversized rodent, but is actually related to a different type of animal. We got a chat going through. Maybe it will actually correct me. Hyrax, Wikipedia. Okay. Yes. It is named after an animal. We do have a we do have a mascot now. For those of you who go to the GitHub page, you'll be able to see the Hyrax wearing a lab coat, which is just awesome. All right, the final project I'm going to talk about today is another thing that's slightly different than what we do, in that it's not meant to address a specific research problem, but really meant to enable setting up new projects. And this is something we found ourselves doing a lot, especially as we worked with the incubators, which I'll describe in a moment. There's a lot of configuration that goes into incorporating best practices into a new GitHub repository. So for example, how do you structure your repository? How do you set up so GitHub will automatically run continuous integration checks or pre-submit checks every time you're trying to push new code? How do you incorporate tools like linting or benchmarking? How do you interface with systems like read the docs or PyPy? And the idea behind Python project template is it provides a very simple list of questions when you're setting up of, what is the name of your project? What is the name of the, contact author? What tools do you want to use? And then it generates all of this configuration for you based on templates. So that way you don't have to go through and remember how do I set up the connection to PyPy? It's just there already. And it greatly simplifies actually starting new projects and working with them. And this has been something that we've just continued to develop as we've gone along because it makes our lives easier. There's an entire Tech Talk series talk about this. So if you're interested in more detail, you can go into a lot more detail with it. We talk about why you want each one of these items in addition to how it sets them up. All right. So that was our core projects. In addition, we run these very focused 3-month collaborations called incubators. And this is our second way of really interacting with the community. They're ways of providing support for researchers at both LSST member institutions and the broader scientific community to work directly with the LINCC Frameworks team to try to apply new tools to research problems. And the goal really is to establish a long-term software development collaboration with the astronomy community. We wish we could do these sorts of engagements with everybody all at once. We try to do as many of them as we can. We run 3 cohorts a year with 1 to 2 projects per cohort. We're currently working on cohort number 8. And so you can see some of the logos that we have. One of the things we definitely do as we start a new incubator is if there isn't an existing logo, we try to motivate having a logo. We really like laptop stickers and try to get people to generate new logos. But we've worked with a lot of really great projects. These are scattered throughout the domains of astronomy, from redshift estimation, orbit fitting, cross-matching, photo simulation. And the idea here really being to try to both integrate with what LINCC Frameworks is doing and also to provide benefit back to those packages in such a way that they can be more impactful and more broadly usable. Selection is done through an open process that's managed by LSST Discovery Alliance, where a committee reviews applications. They're meant to be relatively low stress applications of around 2 pages. And the members of the committee are made up of both people from the LINCC Frameworks team and the broader Rubin community. We look for projects that align with LINCC Frameworks projects and expertise. Ideally, we'd like to have something that works with our software, builds off our software, uses our software, or at the very least doesn't require us to ramp up on an entire new domain where we'd spend the 3 months learning that domain and not be able to contribute. We want to reduce the switching costs. This is a collaborative thing where people from both sides come together. It's not a work for hire where LINCC Frameworks goes off and does something. We have weekly meetings. We write code together. We send reviews back and forth, and we make it a very collaborative process. We look for projects that are well-defined technically and scientifically, likely to lead to outcomes, especially outcomes that are feasible in 3 months. 3 months is not a lot of time, especially when people are ramping up on new code, new astronomy questions, that sort of thing. So we look for pretty tight scoping. And then, as I mentioned, we really want everything we do to be applicable to the broader community. So we try to pick projects which are as broadly applicable as possible. The link off the Discovery Alliance website provides a place for people to apply. It provides the information, a link to the form. You can get a lot more information there. All right, so that is the LINCC Frameworks team in kind of a very high level, very whirlwind summary. How can you get involved or how can you work with us? Well, there's a lot of ways. We have tools. We want the tools to be used. We want the tools to be helpful. We want the tools to be helpful for you to do your science. So you can work with us on integrating our tools into your analysis and trying to solve your problems. We like feedback and feature requests. If there are things that you want that our tools do not do, or tools we don't have, or features you want, this is the type of thing we really want to hear back from the community, because the tools are only as useful to the community as they are to the set of researchers. You can contribute code or models. All of the work we do is open source. It's available for contribution from the wider community. We've had people contribute back to our code base. You could apply for an incubator project and work very closely with us for 3 months. You could give a tech talk like this one. We really want to know what other software work is out there and what other tools are out there that the community could use. This is an opportunity to present work to a broader audience. Or on the more watching side, you could just join our mailing list. Typically, this mailing list has announcements about the tech talks. We do also announce incubators and some other things, but we occasionally have other announcements that go out on it. We have multiple Slack channels where you can interact with the team, ask questions. We have the LINCC Frameworks QA, which is for general questions. The LINCC Tech Talks, which is to announce tech talks and ask questions related to tech talks. And the LINCC Incubators QA. You could also watch a Tech Talk recording. We record all the Tech Talk or most of the Tech Talks and post them to YouTube. And it's a great way to see what other software is out there. Generally, all of this information is available on the website. We'll, I believe, be posting a link to these slides off our main webpage as well. So all of these links will be available. So that is what I have for today. Do people have questions about the LINCC Frameworks team or any of the projects we're working on?
Sounds like
Alright.
Jeremy has covered everything, so there is no questions. Okay, so if there's no questions, thanks Jeremy again for a great talk about LINCC Frameworks, and we hope to connect with you all. And so our next Tech Talk will be October the 9th. We'll hear about follow-up observations of moving object project presented by Carrie Holt. In the interim, please join the LINCC Tech Talk channel and the mailing list Jeremy just listed here. There is more information on the website also. We also have office hours every Thursday at 10 a.m. When this Tech Hub is not happening, 10 a.m. Pacific. So if you have questions about LINCC Frameworks or the softwares we are providing, please join and ask questions. If you have an idea for a Tech Talk, please contact us. And today's Tech Talk will be available on our YouTube channel in a few days. With that, have a great rest of your day. Thank you for attending.